Today's lecture, we know that this is a continued from last Monday. The subject is about calibration with surrogate model. And I repeat this slide that was shown previously. The formulation is that the computer model, including the calibration parameters, is now changed into the surrogate model. And the surrogate model is made by Gaussian process regression. And the next is the model is model. That means the model cannot exactly represent the reality. So usually there is a substantial difference between the model and the reality. So in this case, we can introduce what they call the discrepancy function and make the reality becomes the model plus this discrepancy function. And also this discrepancy, also this is also called by a bias. Discrepancy or bias is modeled by the Gaussian process regression. And finally, there's a field data, which is the observed data. This is given by the reality plus the observation error. And based on this formulation, what we would like to estimate are here. The first one is the original calibration parameter, which is denoted by theta here. The next one is the Gaussian process parameters that appears in the surrogate model of the computer model. And I term them as the beta C, sigma C, and the C denotes the computer. Third one is also another Gaussian process parameters used in the discrepancy. In this case, in the previous lecture, I told you that in order to ensure the uniqueness of the calibration, I set the beta B at 0. So from this time on, I will ignore this one. So in this case, the only parameter to be estimated is sigma B in terms of the discrepancy. And the final is the observation error, standard deviation. All these are to be estimated based on the observed data. In the surrogate model, this occurs when we have the high computational costs. And in that case, we change the original computer model into its surrogates, and we employ the Gaussian process for this. And in order to make this happen, we have to make a finite number of computer model outputs using the sample points that are made by some kind of a design of experimental technique. In this case, we have two inputs. One is original input variable x. The other is the calibration parameter. So from this time, I will introduce uppercase letter x, and that includes the lowercase letter x and the theta. And for these input parameters, we generate number of sample points using any technique. In this case, I just show you the example of Latin hypercube sampling method, and this is the results. And at these points, we run the code to get the output. And we name it as a pair of the computer code outputs, XC and YC. And each are the vector of size m, includes the m number of data. Once we have these computer output data, we can make the Gaussian process out of this data. And the formulation starts from this expression. The surrogate model follows the multivariate normal distribution. So surrogate model is also a kind of random function. If it is not, surrogate model can take any kind of a deterministic function. But in this case, if we introduce this thing, this is no longer deterministic. This is in itself a random function. And within this, we can see two items. First one represents the mean of this multivariate distribution. The second one represents the covariance matrix. And the first one is responsible for the global behavior of the regression. And the second one is responsible for the local correlated behavior. And usually, the covariance matrix is given in this form. By the way, I will call the entire this thing as a covariance matrix. And it will be given somewhere else. R is given by sigma square and Q. So this is R. The R, I will call this as a covariance matrix. And Q, other than this one, sigma C, the Q, I will call this as a correlation matrix. So correlation matrix has no dimension. And the R has the dimension of a variance. So you can make that difference. And the Q is usually given by this form. Within this, you will see here H. I call this as a correlation parameter. And if H is small, we get the kind of an independent process. So the result will be get closer to the classical regression. If H is large, we will get the highly correlated results. And we will get something like a very smooth curve that passes through all the data points. That was the thing that I already taught you. Although this is originally the random function, includes the uncertainty in themselves, but from now, I will treat this as a deterministic function by considering only the mean or the same thing, the maximum likelihood of this. So we will say that in that case, it's a maximum likelihood estimation. We can, or there is a well-established formula in many literatures, even in the HAFTKA's last lecture. The answer is this. We can make a single value once we have the data and put them into here, and we get the solution and use this. Then the result we get is the mean curve of the Gaussian process. And forget the others. We don't consider the uncertainty about that. And if we obtain these values, apply these into here, and using this equation, we get the results. I will show you the example how to process this. By the way, we have to pay attention to this item, QC2. QC is the correlation between any two experimental points given by this equation. In the same way, QC2 represents the correlation between any new points with the existing points. So in that way, you have to understand the meaning of the QC and QC2. The same problem I introduced we have this set of data. And in this case, we assume that these came from the computer outputs. And we'd like to make a good Gaussian process regression only in deterministic way. So we are interested only in having one single function. And the result is this. We don't care about this kind. We don't care about the uncertainty things. Only in this way we go through the process in deterministic way. And in that way, you don't have to go through the Markov chain Monte Carlo. We just use the formula that was shown in the previous slide. And besides, in this case, we can also use this formula to determine the h. In past, I already showed you h can be given arbitrarily, whatever value. If it's small, we have a less smooth. If it's a large or high value, we will have a highly smooth results. But in the literature, there is also the recommendation to use this way. By going through the optimization process, we get this answer and apply this into these equations, and that will be the best response or Gaussian process in a deterministic way. So this is the results of that method. The reason that I don't get any singularity, even with this high value, is because I only make the maximum likelihood curve, not this kind. So for this matter, you can also find out in the MATLAB implementation that I will show you in the recitation this afternoon. So this is the deterministic results. The same way, if we go through the full Bayesian approach, we will get failure. If we use this value, and if we would like to make the large samples of the Gaussian process, we will get failure. So we have to be careful when we use the full Bayesian approach. But for now, we will forget this one. So you just remember only this thing. Based on this understanding, we can construct a surrogate model. The case is this function in this example. And x is the input variable. Theta is the calibration parameter. But in this case, we think these two as the two input variables. This is the graph figure representing the behavior of this function with the theta varying from 0 to 1 with the interval 0.2. But we can also think this as a function in terms of two variables, one being the original x, the other being the calibration parameter theta. So viewing from that direction, we can see the function in the form of a surface or a three-dimensional plot. So vertical is the function value. This is x value. This is theta. And at the value of theta 0, we have this line, which corresponds to this. At the value of theta being 1, we have this line, which is this. Under this understanding, we generate Latin hypercube sampling. In this case, 21 points are generated. Horizontal is x, vertical is theta. And we have 21 points. The idea is to span this whole area as best as possible, using only a finite number of points. And the result is this point. And the output, computer model output is obtained at each of these points, assuming this is very computationally expensive. And this will be thrown away, replaced by surrogates, only based on the finite number of outputs, 21 outputs. This is the idea. This is the results. After going through what I showed you on the deterministic process to get the results, although you see the only apparently the single surface, there are two surfaces. One is the original this function. The other is the Gaussian process approximation, or we also call this as a kriging. So pretty much similar result we will get. Yes?
Do you fix H before estimating hyperparameters?
Your question is whether I fixed H in the process. Yes, I fixed the H value at this value. Also, I should have also went through the maximum likelihood estimation for H. I didn't do that. You can, anybody interested in that, you can go through that way. And I don't know what value it will be. But in this case, I just put arbitrary, hoping that this would generate sufficiently smooth surrogate surface. You can make that kriging using different H values as well, like this. If we use the smaller value, of course, we expect the surface will be less smooth, and the result is this. Further decrease H, we can this kind of very poor surface compared to the original one. So the answer is as high as possible H will be better to approximate the surface, original surface. So in this specific example, we will use this surrogate. And we have already finished the process of this. The level 3 is the approach where only the maximum likelihood estimation is used for the surrogate model. So in this case, at first, we already did this using this example. Surrogate model is constructed using the MLE approach, and plug that into the computer model, throwing away the original, and plug this into that. And go through the process to estimate the remaining parameters in the same way as before. So this is another writing one more time of that. And I already addressed the level 2 in which the parameters, the original calibration parameters, and the bias or discrepancy and the observation error were estimated there. The same way we can make it. Only the original model is replaced by this. The final one is the full Bayesian. Up to now, we ignored the uncertainty existing within this surrogate model. We just thought that this as a deterministic function, but really there exists uncertainty around that. You saw the figure like this. We have this kind of uncertainty. Now we will include even this kind of uncertainty into the whole procedure. And this we call as a full Bayesian approach. And I already told you that this was firstly addressed by Kennedy and O'Hagan back in 2001. The process is extremely complicated to understand. I'm sure if you will take a look at the paper, you will be frustrated. And I don't recommend to go through this process. You just stay at the previous approach. Even the previous approach is already too complex. So this is more than that. First, let us think about the one case. If we would like to estimate only the this uncertainty. Yes?
So you recommend doing the previous approach as opposed to this one. Is there a point in time where you would really want to do this one because you're going to get better results? Like significantly better results?
If we go through this process, can we have the confidence that this will be better than the previous approach?
Yeah, and would it be worth going through the extra complication?
That is a very important question that I cannot answer to you easily. And
I would like to offer an example where it might happen. The model is so, if the model is so expensive that you cannot run a large number of simulations, and then you may have large uncertainty in your surrogate, and you don't have any choice but to do that. That's the one case that I ran into where that was important.
that is a very good answer, I guess. In case of our example, because the example is very easy and simple, we cannot think about that case. But in practice, in the real world, the surrogates approximation is very necessary, and only a few number of the simulations are available. In that case, we will have a large uncertainty even with this case. In that case, we have to go through this process. So if this is the case, without any observation error, without any discrepancy, in that case, we consider the ordinary Gaussian process, including uncertainty. And in this case, the result will pass through the data points, including uncertainty. And this is the central part. This is the most important equation, the likelihood. We use this, and using this, we go through the Markov chain Monte Carlo and get the samples of the unknown parameters, and the rest is the same. And here, YC stands for originally the field data, but in this case, the computer output, this is. And XC is the DOE, experimental points that I explained just a moment ago. So a pair of this, input X and output Y, experimental data, are used in this process. RC, covariance matrix, consists of a M by M matrix. The size is m. And the m stands for the number of computer outputs, computer experimental data. Unknown parameters are the Gaussian process parameters, beta, sigma c. And I don't have to explain one more time about this. The next thing is exactly the same as the level 2. In the level 2, previously, I showed you this equation. In this case, this is the original computer model. And in the plug-in approach, I repeat, in that case, you just replace this by the surrogate. But in this case, we cannot do that. In this case, we have to incorporate this and this together. Uncertainty of the surrogates, uncertainty of the discrepancy and observation error, all together from this time. Anyway, in this case, you just look at this function, this expression, and also identify this pair of data. YF, in this case, this is the field data, as opposed to this one. This one is the computer output. This one is the field data. In this case, the covariance matrix should be given by this way. One for the discrepancy, the other for the observation error. And sometimes, in the other literature, this is also called the nugget term. And the unknown parameters to be estimated in this case are the calibration parameter, discrepancy parameter, and the observation error. So 3 parameters we need to estimate. We will integrate or combine these 2 expressions or equations together. For that purpose, we introduce augmented y. And y includes the computer model outputs, also the field output. Then the likelihood becomes like this. Although the expression looks pretty much similar to the previous one, it is actually much more complex. The basic expression looks the same, but the details are different. In this case, the y is augmented y here, one from the computer, one from the field. And f beta, in the same way, consists of the computer model mean. Usually, fc is set at unit vector. And also 0. The reason we put 0 here is because of the uniqueness condition that I made for the discrepancy. I told you to ensure the uniqueness, I set the beta b at 0. So that's why 0 appears here. R. The augmented R consists of these 2. One from the computer surrogate model, this one. The other from the discrepancy and observation error. All these together used here. And we have all the unknown 5 parameters. And fortunately, we have a MC process. And let it determine. And we will determine the samples. We'll get the samples of all these parameters based on this. You can, if this looks too complicated, you can take a look at the extreme case. By setting these parameters at 0, we will get the same result as the ordinary Gaussian process. At the other extreme, if we set this at 0, then we will get the result of the without including the surrogate, just level 2 results. In terms of the implementation, we need to pay special attention to this parameter, the QC. QC is the correlation matrix between any 2 points. When it is here, the part with the m by m, and this is the region of the computer model output. The 2 points consist of the computer experimental data. In that case, we will have, which is this case, we will have both uppercase xi and uppercase xj. And we can compute easily the values of the matrix here. But in case QC2, because this is the augmented matrix, not only the computer experimental data, but also incorporates the field data. So this part responsible for the computer experimental data. This part is responsible for the field data. So in this case, we need to evaluate this part like this. The row part is the existing computer experimental data points. The column part is the field point. In the field point, we don't have any theta value there. We only have the original x value. So in this case, in the same way, QC2 have the same situation. So QC2, C3, all these includes the unknown parameter theta in their expression. Based on that understanding, we can go back to the original likelihood expression. QC behaves this way. Virtually, QC is a function of theta. QC includes theta as the unknown. So what we see here, we'd like to estimate the unknown parameters using Markov chain Monte Carlo. Within this expression, we can see beta C is found here. All the others can be found explicitly within this expression. Sigma B appears here, sigma here. So this is a function of these parameters. But regarding theta, you cannot see any theta expression here. But as I told you in the next slide, already the QC includes in itself the theta parameter. So this constitutes all the, includes all the parameters that needs to be estimated in that expression. Then the result we get are a large number of samples of all the unknown parameters. And the next step is the posterior prediction. This is the surrogate model. In terms of the Gaussian process regression, the procedure, I always tell you that the procedure is not easy to understand. This is the equation, the mean part and variance parts. So put all these estimated values here individually. Individual value we will get, individual function we will get, and accumulating and repeating all these with the same number of the samples, we will get that number of functions, surrogate models. And this represents the uncertainty of that surrogate model. The same way, the discrepancy is given in the form of a distribution, actually in the form of a large number of samples, the same number of the parameters. So we have that number of samples for the bias, that number of samples for the surrogate model, the same thing. So reality is given in the form of distribution. And the prediction also the same, by adding another observation error. So this is the whole process when it comes to the full Bayesian approach. Next is just an example in the real world. Up to now, I just showed you only a very easy problem, exponential. It was exponential minus theta t, theta x. And from this time on, I will show you some real-world applications. Two things. One is the spot welding. The other is the car crash problem. Spot welding. The input parameters, we have two parameters. The load, the force compressing the two sheets against each other. And the electric current is supplied in the welding process. And the purpose is to fuse the two sheets. And there are analysis program, which is very complex, the so-called multidisciplinary analysis. We should go through that to obtain the results. In this case, the result we are interested is the size of the nugget. They call this as the nugget, the hardened parts of the welding. And they measure this size. And this represents the strength of the welding, and very important in the automotive manufacturing, because there are many spot welding process. This is kind of a typical example of analysis results. Within this process, the painful thing is we don't have any idea about how to impose the proper value for contact resistance between the two sheets. This is the trouble. So because we have no idea how to make this value, we use the field data and inversely estimate this. And this is kind of a calibration. The computational cost is high, 30 minutes for one run. So surrogate model is introduced. 26 design of experimental points are made under these ranges for 3 parameters. I don't know the reason, but in the paper, it says only 14 were successful out of a whole 26 trials. I guess it's like a convergence failure. There are also field data. This is much harder to obtain than computation. And we cannot intentionally design the experiments only for the purpose of validation. So in this case, more or less we borrow or get the existing experimental data. So this is that result. So left side, computer experiments. Right side, real field data. Using this together, we will calibrate or estimate the unknown contact resistance. The result of surrogate model. The output we are interested is the nugget size, and this is a function of the 3 variables. 2 are x, and 1 is the calibration parameter. So 3 parameters model. So we cannot make a 3-dimensional plot because we have 3 input parameters. So this is incorrectly specified. The t should be u here. So when we have a fixed u value, the model becomes a function of two variables, one load, the other current. So we have this kind of output as a result of a surrogate approximation. And the circles represent the computer output data. In this paper, the author emphasizes that the full Bayesian also is available for this, but they don't use that approach. Instead, they go through the deterministic surrogate model. Yes. In that case, they also went through the full Bayesian and found out the results not much different.
Yeah, so that was essentially what I was trying to get at earlier.
But there is another case that is the full Bayesian is also important as well. Yeah. We go through the MCMC, and the unknown parameter u is obtained as a result. This is the results histogram. And using this, we can move to the posterior prediction. So this is the posterior means, although we can also give the upper and lower bounds. But in this case, the figure will be too much complex. So in this type of the figure, we just show you the mean. And also at the bottom parts of this slide, I show a specific case when the load is 4 Newton. And this is the results only in terms of the electric current. This is the simulator surrogate output and upper and lower bound. And also, this is the bias, the mean, and its upper and lower bound. And combining these two, we get the bias-corrected solution here. Car crash, the last example. Simulates the collision of a vehicle against a barrier. There is a famous software, lh17, that was used for this purpose. The computation takes about up to 5 days for one run at the time of 2005. And the field data, already you know, the crashing of full vehicles, very expensive. So the studying this is extremely data limited, both in terms of the computer and the field data. And I have to remark that only for this problem, they don't consider calibration. They already have a certain computer codes or model, and they don't calibrate. They just do the validation by considering discrepancy only. But the procedure is all the same, except we don't do the calibration. Inputs, there are two inputs. One, velocity at impact, at the beginning of the impact. We can impose a certain velocity for that. And the second input is the angle of impact, which represents the three barrier types: the frontal, left angle, right angle. We obtained intermediate output, which is the velocity over time. But the real output we need is the specific scalar quantity, velocity at the time 30 microseconds before the displacement reaches this value. Very important quantity for the airbag design. So we have computer experiments, real data. And this is one input variable. This is other input variable. The barrier type represents the angle of impacts. And this is the initial velocity. And we have 20 experiments, computer experiments, and 30 field data. And this is some of examples of real field data. The left figure is the acceleration, right figure is the velocity, which was obtained by integrating this part. And the two curves represent the two different results. Although it was for the same vehicle, same condition, we see there are kind of observation error with this. Surrogate model is made. In this case, not only we have the normal x input variable, but also we have the time domain. So a finite number of time points are also introduced here. And the surrogate model is made based on this. As a result, this is a conclusion. The high velocity, the discrepancy will look like this. And this is the zero level. And their conclusion is the confidence upper and lower bounds encloses this zero level. So we cannot say there is a specific bias in this case. On the other hand, at the lower velocity impacts, we can see clearly the larger bias, which is greater than zero. So in this case, we say there is a strong bias. And when any designer use the computer codes, this should be incorporated in its consideration. And this was the final results in the car crash problem. With this, I finish my part of the lecture. And during the last preparation of the lecture, there was some more issues that I like to address, but time is too limited, so I cannot show you about this. If you have any further interest or questions, I will welcome, even with the personal communication, this subject to help you better. There are these issues. If you made calibration, can you use it to the extrapolated prediction? This is very controversial issue, and we have to be very careful with that. The same thing, when we obtain the bias, can we use this bias for any other cases? The same controversial issue, and we also learned the overcomes validation metric. And how can we connect this into the calibration? And there is a very interesting issue about the hierarchical approach. We had 3 different barriers, but we regarded it as coming from one parameter, but that should also be carefully treated. If we treat those 3 differently, and then we have to use the hierarchical approach. And also we can have several models, and how do we make decision? Which one is better than the other one? In that case, we have to introduce the so-called base factor, or I forgot it. And this is also an important issue. And there are many other complex issues that we have to deal with, and these will be the subjects not only in terms of the lecture, but also in terms of the research. That will be a very good point for you to explore in the future. this, I will end my lecture. And, this afternoon, I will go through also the MATLAB codes that I made in the recitation. 3 o'clock in the afternoon.